The original idea, I think, was born in South Africa.
With our new hybrid system, we aim at developing compact and efficient cooling systems that are resistant to wind effects, hot recirculation effects, as well as high ambient temperatures.
This product is kind of the first in the world of its scale. So there are similar deluge systems, but integrated deluge system does not exist.
Stellenbosch University and Fraunhofer ISE from Germany, and also our colleagues from Germiston near Johannesburg, they have a strong relationship, and they realized the upcoming call from the European Commission. I organized a meeting in Germany with this core group coming from South Africa and also from our colleagues inside Kelvin and also ENEXIO. Due to the, I think, also relationship in our company and also Fraunhofer, we found a lot of further interested participants, like for mirror cleaning and also for water management. That's, I think, the main story.
Since its formation, Notus has had strong links with the University of Stellenbosch. In fact, one of the owners of Notus Fan Engineering is an active researcher.
We are investigating several technologies within this project.
And this main focus here is to improve the heat exchanger technology. Therefore, we decided to have a closer look on this dry-wet cooling or hybrid cooling system.
The new system integrates the wet part directly into the dry part. So we don't need the surface condenser, the water circulating system, as well as the wet cooling towers.
You can integrate it directly into your conventional air-cooled condenser system. So by replacing one of the air-cooled condenser cells with this deluge condenser.
Then there's a second technology where we develop axial flow fans to improve the fan static efficiency.
Stellenbosch University specifically was chosen because we have extensive experience in cooling system design and analysis.
Let's talk a bit about the full-scale test facility itself. So this facility allows us to conduct tests on two fronts, so it has a dual purpose. The first part is that we have a fan test section. The fan test section is specifically made for a 24-foot axial flow fan.
The research at Stellenbosch has focused primarily on the aerodynamic and the dynamic design of large-scale axial flow fans. And this has led to what you can call a redefinition or a rewriting of the criteria.
The fan itself was developed in cooperation between Stellenbosch University and the Sapienza University of Rome in Italy.
So Notus was in a unique position to manufacture large-scale axial flow fans based on this new design criteria. We don't engage in catalog engineering. We design or optimize the aerodynamic design of our fans for a specific duty point. That is very unique in the market. The rest of the market, you pick a fan off a catalog, but we design a fan specifically for your application.
On the one hand, we wanted to conduct aerodynamic optimization of a fan, so we wanted to create a really optimal fan for the specific design point that it was going to operate at. On the other hand, we also wanted to work on the structural side. So the second part of the design criteria was to design a fan that was structurally strong enough to endure ordinary operation that the fan will experience. But in addition to that, we also wanted the fan to be that its natural frequencies did not coincide with operating frequencies on site.
We did static testing and we saw that the variance was I think less than 0.5% in terms of the natural frequency modes. And then for both of them, they were, I think, more than 10% away from any of the operating frequencies.
We also have a deluge test section or a deluge heat exchanger test section that is downstream of the fan test section.
Specifically for the deluge system, there does not exist a full-scale system. One of the questions that we regularly asked is, what about water retention? And water retention on such a large scale needs to be tested to that scale. So for the deluge system specifically, what we're looking at is how much water is lost due to the flow of air through the deluge system, how much water is retained, how well does the system work in terms of capturing the water again and taking it back into the system. Those are all questions that we can answer by testing at full scale. What we need to take into account is that industry by nature is conservative because they work with other people's money, often it's investors, and those people want to know that their money is well spent. And what you have with a facility like this, you're able to bridge this gap between lab scale, where you almost at academic level, you have these fabulous ideas and the wonderful things that you see into the future, and industry where you want to have, for instance, a power station that runs and works and is reliable. And this facility is able to bridge that gap, literally to a point where you can have people from industry visiting and show them the full-scale application of the system in order for them to assess it better.
Through South Africa leading this project, hopefully they can see the potential that we have as a country. Because in the past we've had the resources, we've had the technology, but now hopefully people can see this again.
Ultimately, what we try to achieve is that we want to have a system that you can control, that gives you sufficient power output during adverse atmospheric conditions.
And therefore we looked for a different solution, and this is this dry wet cooling deluge system, and not having a serious or larger impact on the footprint and also on the investment cost. That was our idea and also the challenge of this project.